So last time we have seen basic concepts of security. We have also discussed very important goals: confidentiality, integrity, and availability. And to be able to preserve or to achieve those goals, we have to use mechanisms and controls and safeguards. One of them happens to be cryptography. So we'll spend a considerable time on this because it is a very widely used mechanism for data protection. So first, let us start by defining what cryptography really is. Any ideas? What is cryptography? Hiding the information, okay, yes? Yes, kind of scrambling the data in a way that if there is somebody listening on an unsecure channel, they will not be able to compromise the exchanged messages. So we have two people who are trying to exchange messages through insecure channel. That's the idea, insecure channels such as the internet. And this insecure channel is shared and public. So others, such as the eavesdropper, they could intercept the messages and misuse them and compromise confidentiality or integrity. So cryptography comes in to help us achieve this secure communication. This is the original goal of cryptography. And it comes from a Greek word. It composed of two parts: crypto, which is secret, and graphy, which is writing. In other words, it's the writing secrets. It's the science of writing secrets. And in the context of computer security, it allows us to send messages, secure messages, using a key. And this we will discuss as we move forward. So the sent messages, only the recipient will be able to decrypt the received message and make sense of it. Any eavesdropper will be just have sad face, they will not achieve their goal. And original goal is to preserve confidentiality and integrity, but cryptography has so many other applications. We use it every day. Believe it or not, almost every daily actions, we use cryptography. So can some of you give us some examples of where cryptography is used in day-to-day life? Yes. Very good, yes. So when you are accessing a website that has, especially websites that have like private information or financial information, or you are trying to log in, you will see that if you look carefully in the address bar, you will see the protocol of communication switches from HTTP to HTTPS, and you might see some lock on the left side of the address bar. Okay, so that is cryptography taking place and allowing messages between the server, the client, and the server. The client being the browser and the server being the web server. All the communication gets encrypted. WhatsApp, for example, like all the messages are encrypted, yes. Even phone conversations, the phone calls, GSM has built-in cryptography, basically, has built-in encryption. So your call gets digitalized, and between your mobile phone and the tower, the communication is encrypted. Every phone call, the communication is encrypted. Okay, any other areas? We all heard cryptocurrencies, yes, Bitcoins and others. Cryptography is becoming even more important because now it's challenging the conventional money system. Okay. Also, you have heard blockchains. It's all based on cryptography. Those are modern applications of cryptography. So it has so many other applications beyond the secure communication. It can also be used for authentication. So, for example, when we want to access a server and we want to make sure we are talking to the right server, we can use cryptography to do so. Okay, now that we understand what cryptography is all about, let's start just having a very broad overview of the field. It's a huge field. Just to summarize it, we will dive into the details as we move forward. So first of all, cryptography area can be divided in two sub-major areas. There is cryptography and there is cryptanalysis. What's the difference? Those are two science areas. So the scientists or people working in this area, they're trying to come up with more and more secure ways of encrypting messages. While the cryptanalysis, they challenge them. And they try to find the ways or give evidence that this can be broken using. So it's kind of an ongoing battle between the two camps for a healthy way, for a healthy thing. Cryptanalysis is not always attackers. Those are scientists also trying to challenge those existing methods. So we are always ahead. And we will see what this all means as we move forward. Now, when we look at cryptography itself, there are three major domains when you start studying this area. There is symmetric cryptography, asymmetric, and protocols for making cryptography works. And for symmetric ciphers, by the way, cipher is the algorithm for doing cryptography. There are so many algorithms out there. Those algorithms to do cryptography, we call them also cipher. It's the algorithm itself. Okay, so we have symmetric ciphers, and those are broken into two major categories, stream ciphers and block ciphers. I don't expect you to get to really understand everything here. I just want to give you the mind map, how we will proceed in covering this topic. So these are the major sub-areas of this big umbrella of cryptography. Okay, let's start with some terminology. You know, every domain has its own terms. First thing, you should learn the terms so you can have meaningful conversations with people in the area. So the first term is plain text. What is plain text?
Like in a raw form?
Yes, very good. The original message. The original message in the raw form before encryption. And ciphertext. What is the ciphertext? After encryption, the result of the encryption is the ciphertext. The encryption is going from plain text to ciphertext, and decryption is ciphertext to plain text. Now, encryption algorithm, what's another name for encryption algorithm? Cipher. So E is the method for encryption and decryption. That's what cipher means. When somebody comes up with some cryptography algorithm or cryptography idea, they have usually like some scientist or some researcher, when they come up with something, they have to do cryptanalysis to provide evidence that this cryptography cannot be broken or cannot be broken easily. Give some quantification of how hard it is to break this crypto system. So, as I mentioned before, so far, except for few algorithms, there is no formal mathematical proof that that these cryptography systems are secure. The only way we can really have some confidence on these crypto systems is that luckily we have some smart people. They call themselves crypto analysts. They look into these crypto systems and they analyze them to give us some confidence, and they try to break them. Some of them, they spend years. That's their job. There are research centers and research professors. That's their job. It's just to try to break crypto systems or give evidence that this crypto system will take 100 years to break. They quantify how long it will take for you. If you want to guess the key, how long it will take you to break. So we get confidence. But cryptography is its deep roots are in maths, like anything, but this one in particular. The people who excel in this area, the innovation in this area came from mathematicians. This is a math area, and as I told you, the people who take math as their major, they take cryptography as one of the courses, if you look at some universities around the world. So crypto is a math-based, and this area is very vast. Some people look at it from purely mathematical, theoretical perspective, but they come up with some ideas that are not very practical in some cases. But some of them, here we are only looking at practical aspects of security, the ones that are used in real life. So originally, cryptography is done by hand. There were at that time no computers, and it was usually, especially in eras of war. When there is war, this is where there is a need. As you know, many innovations and many advancements happen in time of war, and crypto is one of them. The first documented crypto system, it's known as Caesar Cipher. Take any cryptography book, you will find this. This is one of the first crypto systems out there. But it has all the ingredients even for modern systems. So if we understand this, we will get the basic element, what makes up a cryptographic system. So this is at the time of Caesar, 100 to 44 BC. And what we have here is this leader trying to talk to his army and want to send them a message. For example, here, the message is attack at dawn. And when they write the message, the scribe write the message, they will encrypt it and write it this way. And when the army receives the message, they will decrypt it and get the original message. Okay? So in here, if you look carefully, what do you think? How they have encrypted the message?
You change every letter to another letter.
Yes, very good. How they change the letter to another letter?
A to D, T to W.
Okay, so what do you think? Very good. It's a shift cipher. This cipher is called the shift cipher. So all it does, it takes the letters and shifts them by a certain number. In this case, +3. Yeah? This +3 is what do we call it in crypto systems? The key, secret key. That is basically what crypto is all about. Now, what is shared between the sender and the recipient? The key. That's it. So the recipients, when they receive the message, how they will decrypt it? Using the same key, but how the decryption will work? By doing -3, by going backward. That's basically the idea. So that's it. We already have all the ingredients of a crypto system. We have plain text, we have an algorithm, in this case shifting by 3 to encrypt, and going back, shifting backwards by 3 to decrypt. And the algorithm, like we will see later on, we will see as we move forward, it's not important to make the algorithm secret. The algorithm could be public. By the way, all the algorithms we will cover in this course and all the algorithms that are used in all the crypto systems, modern crypto systems are available. You can Google them up, you can find them in books, you can find them in lectures. They are public. Everybody knows them. Their details. What is secret in all the crypto system is the key. That's it. So the idea is to keep the secrecy to the minimum. You don't need to keep the algorithm secret, just the key. This is a very important principle in cryptography. Okay. So, as I explained, in here, the key is very simple. The key is a value from 1 to 26, because we have 26 characters in the alphabet. And here I already explained, you use the key to shift the original message to derive the encrypted message. And the recipients will do the same. They will use the same key, but just the algorithm will be shifting back instead of shifting forward. So let us just take a very simple example very quickly here, do it together. Okay, so we want to encrypt, we are before, we are the time BC, we are working with Caesar and as a cryptograph, and we want to encrypt this message. So, and the Caesar cipher by default, when it was invented, is just 3. Then, of course, it can be generalized. 3 is n, it could be any number from 1 to 26. So let's do this one very quickly. So what we do, we take the letter, we look up its index 0 plus 3, which is this is the encrypted letter. So A will be D. T is basically where is T? 19 plus 3, 22. W. A is again D, and C, F, and K, N, yes. A is again D, W, D is 3, G, yes, thank you. This is D, W, Z, and N, yes, thank you. That's it. Our message is encrypted. Once we receive it, the recipient will do the same. Look up the index of the letter D minus 3 and get an A. That is the basic idea. Okay. Now, if you want to generalize it, let's imagine N here, instead of N is Z. So Z, what is the index of Z? Is 25. So we'll go here 25 plus 3. It gives me 28. Yes? Now 28, I don't have 28. I have to shift backwards. Now to easily do this is I go ahead and do modulus 26. It will give me 2. Modulus, the remainder of the division. And then that's it. We go the encrypted, the corresponding letter for Z is C. So the general formula is you go to the letter, you find the index of the letter, add the key, and do modulus 26. And for decryption, you go to the letter, take the index, subtract the key, and do modulus 26. That's the idea. Now, this simple crypto system, it belongs to the family of symmetric key cryptography. Symmetric key cryptography. Why do we call it symmetric key cryptography? Why do we call this name symmetric, or this term symmetric?
It's the same key, but...
Same key for both sides. Yeah? Same key used for both sides. So, and as I explained, the key is the only secret in the whole story. So whenever we use the same key in both sides, what type of crypto system we're talking about? Symmetric. Now the asymmetric, there is another type of crypto systems. They call themselves asymmetric. Like basically we encrypt with one key and we decrypt with another one. We will see the details of this. So in the asymmetric, we have two keys. One is public key. One is called public key. Public means it's known to everyone. And there is a private key. So I can encrypt by private, I can encrypt by public key and decrypt by the private, or vice versa, in the asymmetric cryptography. So just to summarize and visualize what we have been talking about so far. So in symmetric encryption, what we do, we take the plain text, we use a cipher. What is a cipher? Algorithm, yes. The cipher will use a key to produce the ciphertext. The ciphertext will travel through insecure medium or insecure channel. And then when it's received, the recipient will receive the ciphertext and they will use the cipher decryption algorithm with the same key used for encryption to decrypt it to the plain text. That's basically the idea of symmetric cryptography. If you want to break a crypto system, what you need to break? The algorithm? Algorithm is known. You don't need to reverse engineer it. What you need to break? The secret key. When you are trying to break the secret key, what are you doing?
Brute force.
No. What is the term we use when you're trying to break the key? Cryptanalysis. Thank you very much. Okay, so how can we break this ciphertext?
No, like this.
Very good. Because the keys, the first thing we look at what we call the key space. What is the key space for the cipher Caesar cipher?
26.
26. How many possibilities the key can have? Only 26. Now, manually, if it was a long text, it might take some time to break it. No, even manually, it's quite easy. You can just take one sentence and try from 1 to 26. But in computers, it will take fraction of millisecond to do it. It's one simple loop. Here it is. This is a Caesar cipher. Let me run it first, and then I will explain how it is implemented. This is Python. I am also learning Python. This is the first time doing my first program, but it's super easy. So let's put my program to the test. So we are running a big spine agency. Meet at Aspire Park at 10 a.m. Yes? The key? Any key?
13.
13. Don't worry, this is the ciphertext, and this is the plain text. Okay? Let's say I am cryptanalyst. I got the ciphertext. I know we are in the Caesar era. The only cipher known is the only cipher known is the Caesar cipher. By the way, these days, when you will see later on, even the message, sometimes we receive encrypted messages. Within the metadata of the message, you might even find the algorithm. It tells you, this message, I'm challenging you, it is encrypted with this algorithm. I can even tell you what is the key link. Okay, and if you can break it, go ahead. But in here, it's super easy. All I am doing to break it, I do a loop from 1 to 26, and you can see here, this is still doesn't make any sense. 13, that's it. I know the key is 13. Very easy to break. Brute force. This is a brute force attack. There are, of course, much more sophisticated way of doing it, as we will see shortly. But for this one, we don't even need to break our heads. Just do a loop. It will give you you can break it very, very easily. Okay, so now the reason why we are discussing this is to understand concretely what cryptography means, what cryptanalysis means. I hope now it's clear to you. There's one thing I want to highlight here. There is a special case. Surprisingly, you gave me number 13 as the key. In this system, the crypto, in this Caesar cipher, if you take a message, you encrypt it with the key 13, and then you encrypt it again with the same key 13, you will get the plain text. Just for this key. It is a special case. And in the literature, it is known as ROT 13, or rotation 13. So you can see here, I put here hello. I encrypt it. This is the encryption. This is the ciphertext. I encrypt it again. I get the plain text. Some ciphers have these properties. Just be aware of it. We will see maybe later on some application of this idea, but just keep it in mind. Just happens to be in this particular cipher, there is this special key, 13. If you encrypt with 13 and then encrypt again, you will get back the ciphertext. Just keep this property in mind. We might see it later on. I'll just walk through very quickly because you will have one homework doing something similar. You will implement one simple crypto algorithm that I will discuss later. And you will also try to break it using some kind of code, Python or Java, whatever you want to use. So just to give you a taste of this. So here I'm defining a function. It's called cipher. It takes two parameters, the plain text and the key. Then there is this string library from Python. It's a built-in library. And then I ask this library, please give me all the ASCII code uppercase. So it will give me a string. What the string will have? A, B, C, D to Z. So I don't need to build it myself. It's already built in Python. So what alpha will have, it's a variable. It will have all the English alphabets from A to Z. Okay, the ciphertext, initially I will initialize it to an empty string, then very simple, I go through and look through every character in the plain text, and then look it up in the alpha. Look up the index. Remember, we have a string, and I can look up every letter. When I do find, what find will give me? The index. Now, if the letter is not found, suppose it is a number or it is a space, then I just skip it, which means in the ciphertext, the plain text will be the same as the ciphertext because there is no corresponding letter for it, like let's say space or numbers. Okay, else I apply the formula. I take the original index plus the key modulus 26, it gives me the new index. The new index, all I do, I look up the new index in the alphabet. So for example, if it was A, what was the original index? 0. Plus 3, modulus 26 is 3. I look up the alphabet, what I will get back? B. Now, I do one more trick. If the original letter was uppercase, then I keep it as it is. If the original letter was lowercase, I lower it. You get the idea? Yes. Okay, then at the end of this loop, I have my ciphertext, I return it. That's it. Now, in Python, it happens to be super easy to input. We don't need to do C in, C out, all that stuff in C++. This is simple. Input, I get a message, and then input, I get the key, convert it to int, and then I call the cipher function, give it the plain text, give it the key, it gives me the cipher, and then I call it again, but this time using negative the key, like minus the key. Because for encryption, we use +3, for decryption, we use -3. It's the same algorithm, except the key is different size. This is, I have been working hard to do the encryption, and the eavesdropper, the attacker, it's fraction of a second, they can break it. Loop through every key range, and then basically cipher all of the ciphertext, take the ciphertext, decipher it, decrypt it using the key range, and then look visually work out the key. Sometimes in more realistic scenarios, to be able to do this brute force, you have to have at least one example of ciphertext and plain text and ciphertext. You have to have one example for you to. If the key range is very big, like millions for 1 to 1 billion, you are not going to go through the 1 to 1 billion and visually inspect it whether it makes sense. You have to have at least one instance. Somehow you put your hand onto plain text example and a ciphertext example. Then you can do brute force. In some cases, we will see later on, even if you want to do brute force with the computation we have today, it's not feasible. It takes you years to do it. And that's why we are secure so far. But this notion of security is decreasing every day. Why? No, because the computation power is getting more and more powerful. Computers are getting more and more powerful. So doing this huge number of loops many times, it takes less and less time, to do these brute force attacks. But so far we are okay. Until they invent this quantum computer, still in the labs and research papers. Then we might start to worry. But for now, using the key sizes that we do today, we are fine. And the reason why, just to give you a small example, I think I have one example here, not this one. Yes, here is an example. Just to show you what I mean by this. Anyway, I think this is the comment in Python. So if the key size is 256, suppose the key size is 250, this is the normal key size these days in practical cryptography. Just let me run this. And this is something I was impressed with Python, is the ability to handle big numbers. So 2 to the power of 256, if you want to do brute force, how many guesses you will do to find the key, 1 over this huge number. And how many, if you do want to do brute force, how many times you will have to loop? 1 to this number. It will take you years to do it. So that's why the longer the key, the more secure you are, even if somebody tries to do brute force. But there are other techniques other than brute force. Yeah. Okay. So hopefully you get the basic idea of encryption through this discussion. So let us now move forward. I think we don't need to do this. You got the idea. N is, it doesn't need to be 3. It could be any number from 1 to 25. Okay. Now, if we put the hat of cryptanalyst, we already did. Is this hard to break? Very easy to break. Brute force will do it very easily. Even by hand is easy. By computer is even trivial. We can give it to maybe the students of the 3rd, 4th week of the computer's concepts, they will do it. It's just a simple loop. Okay. This is one example of symmetric key cryptography cipher. The other one I want to discuss here, the first one we saw, what we call it? Shift cipher. We just shift the letters by certain key. Here we have another type of crypto which is called substitution cipher. We substitute letters by another letter. In here, what I do, I get my 26 letters of the alphabet, and I scramble them somehow. And then map the original letter to this rearranged key. Rearranged alphabet. Yeah? So, and then encryption, decryption. Of course, the key here, you as the recipient and me as the sender, we agree on this mapping. So maybe we meet somewhere once. Yeah, and we exchange it. We exchange this mapping, and then that's it. We use it for encryption and decryption. So for you to decrypt, you need to have this mapping. That, for example, here 0, you don't need to put it as letters. You can just put the index. 0 maps to Q. I don't know the Q. What is the index of Q? 16. So you might have a simple table that has just numbers, 0, 16, and so on, just the indexes. And whenever you want to encrypt, very simple, just simple lookup. It must be one-to-one correspondence. Otherwise, it will not work. Each letter mapped to only one other. Each plain text letter is mapped to one cipher letter. And then the encryption is now super easy. I don't need to do any modulus or anything. Let's do this. How do I encrypt this guy? Q, Y, Y, Q. C is what? Is it A? K is V. Again, Q, Y. D is W. A is Q again. And W, I. And N is D, is it? Okay, that's it. This is the encrypted message. The recipients, when they receive it, how they will decrypt it? The inverse. Yeah. So Q will become A and so on. It's very super easy.
But this one can be brute force.
Can be brute force, do you think?
Yeah. With alphabets.
Let's see. How do you think? What do you think? Very good. This is what I want to arrive to. Like whenever you come up, or later, inshallah, you will come up with your own crypto algorithm at a certain stage. If you become some great mathematician, we never know. So what I want to say here, at least for now, when we study some crypto system, we try to, once we understand it, we try to put the hat of crypto analyst and see how can we break the key. Yeah? Now, what do you think here? First of all, what is the key range?
26 above 26.
This is permutation. It's basically you have some letters A to Z.
Every letter has 26.
No, first time you have 26. Then you decided for the first letter. Then the choices for the second letter is 25. Choices for 24. You can this ring something 26 factorial. So how many possible range ranges of the key. How many possible ways you can arrange A to Z? 26 factorial possibilities. Now, we cannot imagine this number, so let's ask our friend, Python friend. Or even I think Java does not help. It gives you that scientific scary notation, but Python just throw it at you and it scares you directly. All right, so here it is. Here it is. Do you think it will be a scary number? You can do brute force on this? Good luck. It still takes a long time. This is a huge number. Very good. We will come to that. Yes, very good. So here, like naive brute force is not a good idea. You will be spending a lot of time doing it. Luckily, there is a better way of breaking this key. Any ideas? Yeah, frequency analysis. No, you will take small. Even if you take small parts, it's hard enough. Have a look. A. How many times we have A here? 4 times. Yes, 4 times. How many we have in the ciphertext? 4 times. 4 times. Q is mapped to Q. What I mean, the language features you have in the plain text are preserved in the ciphertext. Are you following? The language features in the plain text are preserved in the ciphertext. If you have multiple repetitions of particular letter, it will also be same number of repetitions in the ciphertext. Now, these language features, let's say we as cryptographers or as computer scientists, we don't know very well. We'll go to linguists. Linguists, they have some field of study. They call it frequency analysis. Yeah. So something like this. They do some studies. This is what they enjoy. This linguists. You see in a particular language, like let's say English, you take some sample. In these days, very easy. You can take millions of samples, and you do frequency analysis study. And you will see, it's not visible here, but you will see in English, for example, E is repeated the highest, followed by F and so on. So one simple way of doing it, you take this frequency table, this frequency graph, and you do a frequency graph for your ciphertext. And you start to do more meaningful guesses. Rather than guessing a key from 1 to that scary billion number, you are now narrowing the search space. For example, you look and you see, oh, this letter is repeated. This letter is repeated so many times. Q is repeated so many times, and this is an English message. It must be E, or at least there is a high chance it is E. And then you map it to E. So you are doing more meaningful guess rather than just starting from nowhere and guessing from 1 to 26 factorial. You are doing more meaningful guesses, and you mapping the frequent letters you see in the ciphertext with the frequency in the plain text, and it will not be exact, but you are narrowing the search space. Yeah. Plus, not only the language features is not only how many times the letter repeats. There are some language features. For example, very often we have Q always followed by U. So now what you do, you go to a linguist's book, or you study about this frequency analysis, and you study the features of the language, and you try to take advantage of it to help you basically crack the key. That's basically the idea of this one. So you don't need to do brute force because it takes you a long time. You can get help from frequency analysis and make use of the language features to help you crack the key. Trying to illustrate the idea that brute force is not the only way crypto analysts use to break crypto keys, like encryption keys. There are other mechanisms. The most common one is frequency analysis. But basically, we can see here that this system, this crypto system is, this crypto system, which is substitution cipher, is vulnerable to frequency analysis attacks. So that's why this, of course, nobody uses this, but just to illustrate the concept. That's why whenever crypto analysts highlight the weakness of a particular crypto system, it's time for crypto analysts to work harder to come up with a better system. That's the Later on, we will see keys that have 64-bit key, 128-bit keys, 256-bit keys. So some people do some studies. This is what crypto analysts do. They will tell you if the key is 2 to the power, because when you have a key of 64, you have 2 to the power of 64 possibilities. So people do it, and they estimate how long it will take. It will take you a few days. Here it will 2 to the power of 128. It will take you several decades, and 2 to the power of 256. It will take you a very, very, very long time. Except if quantum computing comes, which is doubtful at this stage, still under research. Just to give you an idea that the longer is the key, the much harder brute force becomes. Okay, but there are other techniques other than the brute force. One of them happens to be the frequency analysis, and this is just a brief idea to bring the idea closer to your mind. We are not diving deeper into this. Okay, so to overcome that, the ciphertext preserves the features or the language features of the plain text. To avoid this limitation, this guy, Vigenère, came with this idea. So let me explain it more through an example, and then we come back and see what it means. So what we do in here, we take our alphabet again from A to Z, and we have the index from 0 to 25. And here is the actual plain text I want to encrypt, which is attack at dawn. Then I choose a key. Now the key becomes some sentence, some keyword, some sentence or some text. You give me some other text, and this key is the secret. So here, what is the key? Let's say monkey. So the sender will have the key, which is monkey, and also the recipient will have the same key, monkey, and they will use this to encrypt and decrypt. Okay, so let's see how it works. So what I do, I take the plain text and then take the key and repeat the key to cover the plain text. So here, I come and put here monkey. Here, monkey, it covers for me attack. And then I start again, repeating monkey. It covers for me the rest. I am finished. For example, if I have here at 10, I repeat again. E, that's it. I don't need the Y because I have covered all the plain text. So I basically kind of map the plain text with the repeated key. I take the key and repeat it to match the whole length of the plain text. And then what I do, I take the index of the plain text plus the index of the key modulus 26. Okay, so how it works? So what is the index of A? 0. What is the index of M? 12. 0 plus 12 is 12. Modulus 26 is 12. 12 modulus 26 is 12. So I look up here 12, and basically my cipher letter will be M. Are you following? Okay, now T. What is the index of T? 19. What is the index of O? 14. Okay, 19 plus 14 modulus 26. Is it 3? Okay, good. Are you sure?
No, it's not. No.
19 plus 14. 33 modulus 26 is basically 7. 7, yeah? Okay, so 7, look up 7 here, is H. Can you see it? And T, I cannot say, oh, T, I have done it, I have just done it, I know the index will be 7. No, you have to do it again because it's not mapped to the same letter. This is the same idea, it's not mapped to the same letter. Every time it could be mapped to another letter. So we have to do here, T is 19, and N, 19 plus N is 13, yes? 13 plus 19? Sorry? 32, yes? 32. 32 mod 8, mod 26. So 4, 6. Look up 6 here is G. You already see the power of this system. The language frequency is no longer preserved, or at least no longer fully preserved. Because first time T is mapped to H, second time is mapped to G. Frequency analysis, what it's doing now, is crying. It has to think harder now for other more sophisticated technique to crack the key. Much harder, you see. But we had to wait many centuries to come up with this idea of taking the key and kind of replicating it to match the whole length of the plain text and then do the encryption by taking the index from the plain text plus the index of the key, the sum of the two, modulus 26, to come up with the index of the ciphertext. And we keep doing this all along. Few messages, this can change this. You get the idea of the Vigenère cipher. So Vigenère cipher, we no longer map the letter, always map the letter we no longer map the letter from the plain text to the same letter in the ciphertext. We don't do that. Using a key that we replicate allow us to have different mapping. Every time the same letter could be mapped to different letter, making cryptanalysis much harder. It is still feasible, bit of cryptanalysis is still feasible, but much, much harder. Because unfortunately, once the key repeats, we might come with the features of the language appear again. But they don't appear as bad as in the first system. You see here, second time at with M, it gives us M, which is the same cipher letter as the first occurrence. So you will have some mix. It depends. Some of them will be mapped to the same. Some of them will be mapped to different letters. Okay. Now, I already mentioned this. This is a very important idea from Kerckhoffs's principle. What this guy is saying, in crypto system, we don't need to secure the algorithm. The algorithm could be public. We only need to secure the key. The secrecy is in the key, not in the method. And this principle, also known as do not rely on security through obscurity. There are many crypto systems out there, well documented, where they try to rely on making the algorithm secret, but with time these algorithms were cracked, reverse engineered, or somehow cracked. So and plus to keep an algorithm secret is much harder than keeping kind of a small key secret. It's much easier to keep the key secret. Okay, so far, these are still not perfect. Brute force is much harder. The frequency analysis is also much harder, but feasible. And then we come to a one-time pad. This is the last one that we will cover in the classical historical ciphers. In the one-time pad, what will happen is similar to the substitution, but basically we generate a key the same length as the same length as the ciphertext. Sorry, as the plain text. The same length as the plain text. So if we need to encrypt this message, let's say this message has 20 characters, the key will be 20 characters. If we want to encrypt a message with 1,000 characters, the key will be 1,000 characters. And we use this key only once. Now, imagine the scenario where we have spies. You know, spies, this was used, by the way, in the World War I or II, where basically you have a book that has the keys. And this book, maybe it has dates. Each day we will use a different key. And basically when you want to encrypt a message, you look up, you take your book and you take a chunk of the key and you use it to encrypt. And then you cross it. Say, I will never use this again. And when you send the encrypted message, you somehow communicate with the recipient. By the way, the key is on page 25 from this place to that place, for example. So somehow there is already kind of pre-printed list of keys that are shared between the parties. Every time they send messages, they use part of the key and cross it. They will never use it again. You can see this is also very fragile. This is very secure, 100% secure, cannot be cracked whatsoever. But what can be cracked in this case? The book. If somebody managed to get hold of the book, the whole system is broken. Yeah? So that is basically the idea. All I do, it is very similar to Vigenère cipher, exactly the same algorithm. The only difference is that the key is randomized, or not really randomized, it's kind of agreed upon previously, and the key length is the same length as the plain text. And the algorithm is the same. Basically, you look up the index of this letter plus the index of this letter, modulus 26, and you do the encryption that way. And the recipient will do the practice. If you look at the history of this method, the recipient and the sender, they have basically these books. And by the way, if you see this, even World War I or World War I or II, these documentaries, you will see some communication center. This communication center that send or receive messages, they might have the book, let's say, in front of them. Imagine they have the book in front of them. Of course, if somebody managed to get hold of the book, everything is broken. This is not practical in the computing sense. But the concept, we will see some of the concepts has been made more practical through more smarter mechanisms. And I will see you next time. We almost finished the core idea. Inshallah, from next session, we'll try to start looking at modern cryptography used in the real world. But we are now equipped with the basic ideas, what it all means, what are the challenges of the keys and the crypto analysis. Okay, thank you and see you next time.